Welcome back, students. Let us now go into section 3 of this notebook, arguably the only topic that is directly related to rest of Calculus 1. The other topics, the other sections of this notebook, sections 1 and 2, were as a matter of fact stepping stone towards section 3. And also there are some geometrical aspects of vectors and dot products that we covered, but in Calculus 1 they are not that important as a matter of fact. In Calc 3, of course, I'm going to emphasize those, but in Calc 1 level, not very much, unless most of the students are going to engineering program or something. Still, I thought it was nice to give you a preview of what's to come in Calculus 3 because I had been repeatedly frustrated in multivariable calculus 2730 that students didn't have good intuition, geometrical intuition, because they didn't learn anything related to vectors a priori. And with early vectors and showing some 2D vectors in advance in Calc 1 will definitely help you in Calc 3. Okay, let's begin vector functions. Vector function is basically a function given by vectors, or equivalently a function given by pair of two functions, x of t and y of t. Geometrically speaking, we begin with a position vector. You see, what was a position vector? Given a point x comma y, we can get a position vector that starts from the origin and ends at point x comma y. So the point x comma y and the vector x comma y were interchangeable, and that's how the position vector is working. And you can use vector function to this position vector, then x will become a function, y will also become a function, and as x and y change, the tip of this arrow will move around. And how do we visualize that? The best visualization I can think of is moving particle model. And here's an example. The simplest example is here, a line. Vector p of t is p0, which is starting point, black point right over here, that's constant, plus t times v, and t is a function, and v is a vector a comma b. So if I express those in pair of functions, you're gonna get x0 is t times a, and y is y0 plus t times b. We have pair of linear functions, and not coincidentally we have a line. Linear functions give line. What a surprise. This is a moving particle model basically. The particle is on the tip of this red arrow, and red arrow is the position of that particle, position vector. And the particle is moving along the line because the direction is the same, the v. So blue vector v, a comma b, is the direction vector, and through that direction the point is moving and consequently generating a line. Easiest example, the simplest example. Next example, an ellipse. A cosine of theta, b sine of theta, where a and b are different, and then we are going to end up with an ellipse where a is radius in horizontal direction and b is radius in vertical direction. In this particular case, b is bigger, so this picture, this ellipse, is elongated vertically. And this one is the moving particle model or moving arrow model. Particle is moving along this ellipse, and the position vector is this red vector. And black point is the center. And the student who remember analytic geometry will recognize that these 2 points are the foci of this ellipse. Okay. There are even more spectacular example like this one. Here, vector function is given as x of t comma y of t, and x and y are really complicated, but complicated with a lot of sine and cosine, and sine and cosine are periodic, so you expect a closed curve. Indeed, you have a curve like this, which is aesthetically beautiful. I named it flower. And this is a moving particle model. I may have to slow it down. Red point is the particle, and red arrow is the position vector of that particle. And the blue curve is a trace of that moving particle. And that's how a vector function generates so-called parametric curve. T is called parameter in geometry, and x and y are, of course, x-coordinate and y-coordinate. So vector function and parametric curves mean the same thing, actually. Vector function is dynamic, parametric curve is static, because you're looking at only the trace after all the motion is done. This one, I named it butterfly for an obvious reason. Again, let me slow down the motion. The red point is a particle, and trace of that particle is the blue curve, and the red arrow is the position vector. So if you look at the change of red arrow, you're looking at the vector function. Now, if you look at the red point and the trace of it, which generates this blue curve, that's parametric curve. And this animation shows you that they're the same thing, actually, interchangeable concept. Okay, did you enjoy some examples? I hope you enjoyed at least some aesthetically beautiful examples like C and the D. These examples are not as aesthetically pleasing, but simple enough that you can actually handle with paper and pencil computation. Plot a parametric curve and then eliminate the parameter to find Cartesian equation. Well, the first problem is extremely simple because I can eliminate t really easily because x is equal to t. So substitute t equals to x, I'm gonna get x squared minus 2x minus 3. What is this? Y equals x squared minus 2x minus 3. That's a parabola, isn't it? Graph of a quadratic function. Yes, it's a parabola. In terms of parametric curve, however, you end up with this kind of moving arrow model. Trace of moving particle, where the black arrow represents the position vector as a vector function. Let's go over to less trivial model. How about this one? Oh, I take it back. This is not really less trivial. I mean, x equals the square root of t. That's right. And I don't have square root of t, I just have t. So all I have to do is replace t by x squared, I guess, because from here I'm going to get t equals x squared. Indeed, like this. And this is going to be a curve, but there's a bit of a catch. We're not going to have entire parabola y equals 1 minus x squared, because from here I can see x is always non-negative. Indeed, here's the plot. It's not the entire parabola because x cannot be negative. X is square root of t, that's always non-negative. Here is the moving arrow model. Moving black arrow represents the change of position vector or the vector function. And trace of that tip of the black arrow is the parametric curve. Those two are too simple. Here's a bit better challenge. How do we do this? Is it possible for us to solve for theta and plug in? That's gonna be pretty hard because you have to solve for theta, then you're gonna get arc cosine over arc sine, and that's gonna be a mess. There's a better way though. We can square them, and we can use cosine squared plus sine squared is equal to 1. What am I talking about? Oh, let me show you the plot first. It's going to be an ellipse. And here is the moving arrow model. Okay. How do you know this is ellipse? Well, the kind of tool that you can use is cosine squared of theta plus sine squared of theta is equal to 1. Pythagorean identity. And how did anybody think of this? Well, there's cosine, there's sine, and you have to think about all kind of trig equations or trig identities, excuse me. And this one really stands out because this one has both sine and cosine, and this is arguably the most important trig formula out there. So that's what we're going to exploit. Here we go. Divide by 3, I'm going to get x over 3 is cosine of theta. Divide by 2, I'm going to get y over 2 is sine of theta. Now square them both. Why did I square them both? Because I wanted to add them up later. Square them, I get x squared over 9, y squared over 4. Add them up, what do I get? I have to get 1. Consequently, we have this equation, x squared over 9 plus y squared over 4 is equal to 1. This is an ellipse. Likewise, you can handle these kind of problems. And these are going to be more challenge because it's not going to be easy to solve for t and plug in. And I don't know that is even possible here. In this case, okay, it may not be impossible because y is equal to t squared, so t equals to be square root of y, and you can use some, but you have to be careful about positive and negative, of course. But this one, well, how to solve for t and plugging in, that's going to be a challenge. Or do you have to use alternative technique like something like this? Well, I'll leave that exercise to you. As a matter of fact, this notebook has the answer, but I'm not about to show you. Instead, let me just show you a plot. Interesting, we have a circle. And this is a moving arrow model, which is actually partial model. Very different from the ellipse you saw before. The speed of this arrow, or the angular speed, changes a lot. Around -1, 0, very slow. Around 1, 0 here, very fast. As a matter of fact, looks like this black arrow is jumping. The reason because it looks like it is jumping is because this program is incomplete. Theoretically, it takes infinite amount of time to precisely reach -1, 0, but nobody has infinite amount of time, so I just cut it off. And then starting all the way past -1, 0. That's why looks like we're gonna have jump here. In reality, there's no jump. It's just that the arrow slows down so much that it takes infinite amount of time until it theoretically reaches -1, 0. That's the kind of effect you're seeing. Exactly how you get this circle is left to the students. The answer key is here in this notebook. It's just that I do not want to spoil the fun.